Hey everyone.
Greetings, guys.
Welcome.
Mm-hmm.
Welcome, folks, to another episode of Eigenbros.
Mm-hmm.
Today, Terrence was grilling me on my research project.
Not really.
Not really
A light
Inquisitive.
roast.
Yeah. He was inquiring in
Not
basically
even
what
roast.
I've been studying for the past year and a half or so.
Yeah.
And hopefully I answered him pretty succinctly. I think.
Yeah, it's pretty interesting, I thought.
Yeah, my project deals with anomalous transport phenomena in this certain iron compound that I grow.
I'm hoping that the layman will get something from this because it was a little bit higher level than normal, I think, because it got a little bit unhinged with the terminology at the end. And even, condensed matter, non-condensed matter people will hopefully understand. I think so.
I think so.
Yeah.
I think I defined my terms a little bit carefully. I tried not to lose sight of the bigger picture in some sense, and so hopefully you guys learned something interesting. I certainly did with this particular topic. It's super interesting, at least to me, obviously. But yeah, if you please like, share, and subscribe with anybody that you know. If you know anybody that wants my crystals, let me know.
Juan is selling meth.
I am. I'm a crystal. I grow these compounds: iron 3, germanium, tellurium 2, and then iron 5, germanium, tellurium 2. So if you know anybody that wants some of those, I have them. So
Crystals on deck, baby.
I have some fresh ones too that I just grew and I had to take out today. So anyway, yeah, like, comment, subscribe, share. Follow us on Twitter.
Yep, follow us on Twitter. Follow us at Instagram. So Twitter is Eigenbros. Instagram is Eigenbros as well. We have TikTok, Eigenbros2. And then also check out the website, eigenbros.com. And I think that's it.
Yeah.
See you in a bit.
Okay. 3, 2, 1.
Hello, ladies and gentlemen. Welcome back once again.
Welcome to another episode of Eigenbros.
Mm-hmm. We've got Master Juan here.
Yeah, now you're talking to a master. Please respect the labels and the certifications.
Mm-hmm.
I'm going through a bender right now.
A bender?
Yeah, a bender. Just like coming down from typical graduate student stuff. You leave most of the work till the very end.
True. You're on your come down right now.
Yeah. Right now I'm coming down from like the week. The week was very like up and down. Couple hours of sleep, maybe 6 on average, which is better than most.
Yeah, that's
But
actually
in grad school, for the most part, I've managed it pretty well. But past couple days, I was like, man, 4 hours, and I was just like, just because you're, you get nervous and anxious leading up to your like defense and stuff, and so I was. Oh, and then yesterday I woke up in the middle, I woke up at like 6 a.m. and I was like, man, I guess I'm awake now. And then we were up.
That wasn't out of sheer productivity?
No, it was just like, man, I guess I'm awake. I don't know. And then
now remind me, Juan, my time skills already fucked. The defense was yesterday or was it Monday? Monday, okay.
So for those of you listening, it was the Monday that this is posted, and yeah, it went well. At least the talking portion, the public portion, and then the closed doors stuff was kind of I think it's run of the mill kind of like defense kind of stuff where the professors ask you like, what the hell is this? And
right.
Then they try to really test that you know what you're talking about. The thing with me, though, was I think I got a little bit of flack because my topic kind of I did a lot of stuff.
Yeah,
in the past
you
year
were
and a
mentioning
half.
that you did like a real broad amount
like
of topics.
four topics. And the committee was concerned, well, you're kind of doing all this stuff. We're worried that you don't know, like, you only know a little bit about a lot of these. Well, you know a lot, but a little about each thing.
Right, I guess they thought you were spread too thin, correct?
Yeah,
Is that accurate to say?
Yeah,
okay.
Pretty much. And so they were like, well, we're concerned that for some of these bigger topics that you're on now, like I study basically the topological nature of magnetism in this particular compound that I have, or that I grow, these 2 crystals. And, it's kind of they were a little bit concerned, like saying, "Oh, well, we don't know. Like, can you have a conversation with the theorist in the group in this committee. And then I was like, I was like, with confidence? I don't know. Like, it's a discussion.
Can you ever have a confident discussion with any theorist professors?
That's the thing. Like, I was like, that's kind of a loaded question.
Yeah.
Because of course I'm a lowly graduate student, and I can contribute and I can talk about this. Well, no, sorry. I can talk about this and discuss it with the professor, but I don't know if I will be able to add anything.
Yeah. I'm sure some theorists out there would think they can go toe-to-toe with professors, though. I've known many.
Oh, some theory students, you're saying?
Well, I mean, even just normal graduate students, I think some of them feel real comfortable with sparring up or squaring up, let's say, with professors. Personally, I never got to that level. Of course, I left graduate school earlier than most. Well, I don't know if the most, but I left graduate school early, so I never got that ability. But I'm pretty damn sure you're not.
Yeah, but you're not. But you weren't that confrontational either in classes. Like most of the theory kids are very like, they'll call the professor out if they see something that's wonky or not ill-defined or something. You know what I'm saying?
I was mostly just asleep, so.
Those two aren't correlated. The reason why Terrence left in the sleepiness. It was just because Terrence believes in not drinking coffee.
We already went through this.
We did.
Remember we had an episode where we were talking about, is it necessary to drink coffee?
Oh, in grad school? Yeah.
Yeah, man, bro, I don't need coffee.
Okay,
man.
all right. But you were sleeping, bro, while I was wide awake.
I was sleeping because it was boring.
Yeah, and my anxiety levels were through the roof at the end of the night, but, and I couldn't sleep. But, hey, I'm listening, okay?
See, I slept like a baby. As soon as my head hits the pillow, man, I'm fucking zonked.
Ooh, my bad. Sorry for those of you that don't like listening to, digestive noises.
It's a 2-for-1 podcast, mukbang podcast.
Gotcha.
Right?
Yeah. Like it's like.
Or is there one for slurping?
I'm sure there are people out there. Like I knew somebody that vehemently did not enjoy any kind of like mastication noises. You know what I'm saying?
I think a lot of people aren't into that because it's kind of a podcast rule: never eat on the mic.
Yeah.
Have you heard that?
Yeah, obviously, but it's more because it's like just the constant repetitive noise of hearing this thing. Like, it's like, it's just like.
I've never been bothered by it though, honestly.
No, I've been annoyed by it, but I wouldn't say it angers me to an irrational level that some people have.
Okay,
you know what I'm saying?
It's a spectrum, right?
Yeah,
a rageometer, if you
will. Yeah. Well, like speaking of rageometer, it was. So yeah, the professor, one of the professors asked this question, and I was like, no, I don't think I can like really add anything, but I can definitely discuss the topic, and yeah, like I'll definitely I don't know the theoretical nuances of some of this stuff, at least really well, like mathematically fleshed out. Where I'm,
Shit, I did not start the clock again.
No, we're fine. We got to watch here. Like,
what's your time?
You see down here? 6 minutes.
6 minutes. Okay, I'm just gonna start mine late. But go ahead. I'm sorry, Juan.
But yeah, it's just it went well. I think they probably gave my advisor a little bit of a beating over the head because they were just like
you were saying.
Yeah, I think because like they like they were saying there was just like a really broad like kind of topic and a lot of data that was taken. But it's like. Also, my advisor's trying to go for a publication, so we need so much supporting information to really say something. But then, what we have seen, I don't know if this is indicative of every other project that people do, or most other projects in graduate school that you might do, depending on your advisor, right? But we were worried that we didn't have enough information that referees were going to, how would you say, sideswipe us. They might hit us with well, this is not. You collect more data, take more data, blah, blah, blah. We wanted to preempt that and have a lot of supporting information to say this particular thing. But what we've seen in a lot of other papers that have been published for my particular crystal that I'm growing, it's most people just report their findings.
Right.
And then that's it. But he wants to I think he wants to go for a higher profile journal and stuff, which I commend. But,
which means what? You have to delve into the theory a little bit more.
Yeah. You'd have to get theorists on board to look at the data and then like make up their mind, fit models and stuff. And the thing is, we can all do that in house, but it takes time.
Yeah.
Like, and there are other groups that might be doing the same thing, and then you just really. You look stupid at the end of the day when you
have nothing to show for
it. Well, the thing is, like, that's kind of what happened to me. It was a very popular compound at the time that I jumped on board. I think it was late 2018. It's iron, germanium, tellurium in the stoichiometry of 312. So three iron atoms, 1 germanium, and then 2 tellurium.
Okay.
And so like
what, Fe3
GeT2.
Okay.
Yeah. Iron, germanium,
Vegeta?
Iron, germanium, iron, germanium, ditelluride.
Okay.
If you want to get into the chemistry stuff.
Wow, you actually know the names. Impressed.
Yeah. I'd have to, but I honestly, a defense one went weirder than I thought. Because usually I was expecting it to be more based on the content. Mm-hmm. And some of it was, they were getting hung up on certain parts. But I thought they were going to grill me more on my manuscript. They were like, the formatting on your manuscript is kind of like jacked up. They're like, you need to fix that. And then they're like, well, editing, like there's some run-on sentences here and there.
Yeah.
But they were editorializing and like they were saying some stuff. They were mostly just complaining that it was too long. My manuscript was too long.
Oh, really?
Yeah.
Is that just because of the breadth of topics that you were doing?
I think so, yeah.
Okay.
Yeah.
So actually, Juan, I guess for the layman in the audience, you might want to explain the process of how you even were able to defend your master's even during the COVID situation, because I know, as some of our viewers know, we're in Florida, and things are kind of ramping up pretty heavily down here, COVID-wise, and everything's shut down. So I guess like. What did you do to even present?
What did I do to present? I initially was supposed to defend in the spring, but COVID happened, and so a lot of dates got shifted around, and so yeah. By the time in March, I think I had like a decent draft of my manuscript, but like. My advisor kind of wanted to add more data. I was like, man, we're definitely like, we're doing too much, man. We're overdoing it. I literally said, I think this is going to be overkill, but hey, you're my advisor. I'm going to lean into your wisdom a little bit, So yeah, it was, so he was like, no, we got to get more data to support our sort of findings. And I was like, okay, I mean, yeah. Look, you know more than me in this respect. I can read papers and survey papers and be on board with you about where I think the project should go, and pretty much I agreed. Like, there's been very little disagreement about what measurements to do and what measurements not to do. Either way, I was on board, took a little bit more data, finished up the manuscript stuff, and then so the summer I had to spend studying for the comps a little bit, so I kind of had to divert time to that. But then at some point, I just completely shifted into trying to get this master's thing finished and completed.
And now you're there.
So now I'm there. It's been a ride though, because it's not. How would you say? It wasn't easy during the COVID thing, mostly because just navigating. Things don't go as quickly. Collecting the data we needed wasn't done as fast. And then you're waiting on data. At the very last, like a week before, we were waiting on data to be analyzed so we could include it in the presentation.
Right.
And I didn't want to do that, but he was adamant. He was like, we should do it. And I'm like, oh, man, I mean, I don't know. But yeah, that's probably going to happen. That depends from advisor to advisor. Some advisors might be like, that's fine. We can stop here. And we'll go from there. But
now let me ask you this, Ellis. So I kind of was wondering, so of course I know already, but so when you presented though, you did this via a Zoom conference, correct?
Yeah.
So could you just tell a little bit about that? Like how was your committee even on there? Like who was on the Zoom call, what it consist of, and what was the whole process behind it?
Oh, I see. So yeah, I mean, you just kind of schedule like I just scheduled with the committee. The coordinator for the student program, and then you sent out everybody in the department, you sent out a public email saying, "Hey, guys, ladies and gals, come to my..."
Ladies and gals.
I mean, sorry.
Ladies only.
Ladies only. That's what I meant. That's what I sent on my email. Ladies only, please.
You see where Juan's mind's at.
I'm sorry. Yeah, I'm a little bit. This is why I'm trying to finish my coffee so I can like get a little bit more accurate in my language. But yeah, I was like, gals and guys, like, come see my, and they them's come see my my talk. You know, and they sent it out over the weekend. Monday came. Pretty much, I made sure to send reminders to the professors both Monday and then Wednesday, reminding them that this was still going to happen and then that the time was still okay. My time initially got shifted up, and I even had a medical emergency with one of my committee members, so there was some shuffling, but they were still able to work it out.
Mm-hmm.
And yeah, it was kind of hectic, but locked in the date and kind of kept my sights on it, and then the day came, and yeah, I practiced multiple times.
How many people did you have on your committee?
4.
Okay.
4 technically.
4, including your advisor?
Yeah.
Okay.
So,
and that's pretty standard, correct?
No, well, for master's committees, not necessarily. I think it's 3.
Okay. So why did you have 4 then?
Because politics in the in our department, I think. Because
we got to keep an extra eye on Juan.
What do you mean?
So we need to add a whole other person.
I know, yeah. No. It was it's because of politics. It's mostly like the without giving too much information about or details about the inner workings of our department. There are research scientists, and then there are like the academic faculty.
Mm-hmm.
There's kind of a divide between, at least there's a perceived divide between research scientists and academic scientists. Meaning tenured faculty.
Yeah.
What I mean by academic, full time, and there seems to be a gap there that is sort of left unsaid. It's kind of understood to just not really be discussed or brought up.
But everybody knows it for sure.
But everybody knows it, and no one really says it. And yeah, it's interesting. It's an interesting thing, but basically that's kind of why they require, like, at least for students that work in the same research laboratory that we have access to, a lot of the physics students that have access to it, we have to get an extra committee member. So yeah.
I see. So it's just from your circumstance.
Yeah.
Okay.
But
cool.
typically I think it's 3.
Okay.
3, 1 experimentalist, 1 theorist in your field, 1 experimentalist in your field, and then another professor in your general, how would you say, in your department. So, yeah.
So it has to be your department. It can't be someone like a mathematician or something.
No. That's for your PhD. You can do that.
I see.
Yeah.
I see. So the master's is a little bit more limited in scope.
Yeah.
Of who you can actually have on your committee. Okay, interesting.
Mm-hmm.
So then once you had all your stuff set up, you did the Zoom call. How was trying to defend on Zoom?
It was honestly, I think it went a lot better than it's because I had practiced multiple times, and I was already comfortable using Zoom because in-person talks are a little bit more, there's a lot more, how would you say, body language, I think, is like really clear in person, and I think it's a lot easier to be less harsh in person. So I was a little bit concerned with professors kind of nailing me on the cross.
Because they felt a little bit of more of a disconnect.
Yeah. And I was worried about that. And I didn't sense that energy because they were all very accommodating in some sense. Like, they know this is a pandemic. They're like, yeah, like, this sucks. Like, we know it's not a traditional way to do this. But yeah, they were for the most part kind of... I think they kept it pretty normal, at least from gauging from what different people have said about. We know a lot of PhD students, and they just say, like, yeah, that's kind of how my prospectus went.
Okay.
Like it's expect for the professors to push you and push your buttons and say things that might instigate you or something.
Mm-hmm.
Yeah, and so
But when you went in, did you feel pretty confident, or?
Yeah, I think I did. Mostly because I had already prepared, I think, adequately. I spent like the last 3 weeks pretty much trying to nail it.
Mm-hmm.
You know.
Did you? So sorry to interrupt a little bit, Juan. I just want to. I'm kind of curious.
Please suss out anything because I feel like I could talk anything about the process. I might be.
Yeah, I'm kind of curious because I mean, of course, since we're living together, I saw a bunch of your stuff going on, but I still didn't see everything. Like,
mostly isolation in my room.
Yeah. So I know you had a speech and everything, like a script prepared. So I didn't see though you actually like having to practice your script. Did you have to run through your script a lot, or what was your process behind actually keeping your thoughts together for the presentation?
So Terrence is of the mindset. I think you were like, bro, just go for it. Use your plot points. And I think I tried that.
Yeah.
Initial runs, and then my advisor was like, no. You're too.
So he vetoed it.
Yeah, because he was like, "You're too scatterbrained."
I see.
Like you're gonna be like, "Well, there's an interesting paper that this," and I'm like, "Oh God, I'm doing it again," and I'm just like, you know, and it's bad. Like if you're like Terrence and I, where you have this.
Maybe mine sounded good in theory because we both, just for an MBTI callback, extrovert intuition off the rails.
Yeah. It's supposed to be, when you're more mature, it's supposed to be an organized chaos, but it's like when left uninhibited, it's just like, but
that's why I think the outline should help, because the outline gives you a kind of what do they call, like the gutter guards in bowling. So you at least bouncing off, but you're bouncing off the gutter guards. You're still within the parameters.
True. Yeah, I think that works for somebody who has a mastery of, I think, that function or that of cognitive ability. But the thing is, for me, I am such a digester of See, I'm doing it right now. I'm thinking about how to say things before I say them.
Yeah.
Like I pause and
it's like the Obama style. You gotta.
Yeah, you gotta think before you say. You gotta read.
That's probably why you do the impression so well.
Yeah, because I know how the pregnant pauses that he takes.
I
understand them. I understand where they're coming from. I do the same thing. And so for me, because I think this way, I kind of, I know that I knew that I had to guide it in a more scripted way, and it's just why I have to follow a script. Because
how to a T though?
It was more like a guidance. So sometimes I would go off the diagrams and read off the figures, but sometimes when I'd be thinking a little bit about this thing or imagining it as I'm saying it, I would kind of get lost and kind of want to go on a tangent a little bit.
Then you just start having to rein it in.
So then I have to rein it in. So then I have to be like, anyway, this particular thing, blah 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 blah. And so so it served to collect my thoughts. Now some people might just I think Zoom made it easier in this case too, because I didn't necessarily have to memorize my script to a T, because you could go into presentation mode, and then you can kind of read your notes if you have any. Yeah. And so I generally use that to kind of like the notes to kind of guide me, like make sure to talk about this and that.
Now, a question is that I have a follow-up is, do you think that the podcast has helped you at all in your ability? Yeah,
my ability to talk on screen and off screen. Yeah.
You think it actually has?
Yeah, on screen for sure. But I've never been really shy or had any stage fright in some real sense.
Because remember in the beginning of the podcast, you didn't even want to do video. Do you remember those days?
I didn't, because I didn't want to be seen mainly.
Yeah.
Yeah. I just like, nah. I don't, the perception part, I don't want to be perceived.
Oh, I see.
I just want to be heard.
Yeah.
I want to be in the shadows, but you can still hear what I'm saying.
That's the introversion.
Yeah, that probably is the introversion. Yeah, and so, but yeah, I think for the most part it was it was nerve-wracking, but by then the whole point of practicing is that you kind of just you get the nerves out of the way and you feel confident enough to say what you need to say. And
so you came in pretty solid then.
Yeah. I was just more nervous about the type of questions they would ask, and so I went back and reviewed all the concepts that they might ask about. I think I was discussing with Terrence, like fundamental like stuff that we even like sometimes debate
Some
about.
brutal questions that I couldn't even answer.
Yeah, some like real foundational stuff, and then like.
I don't think I was much help.
Well, they did ask.
tried,
They did ask, like, for instance, like they were like, "Well, what do you mean by like, for instance?" Because I used the phrase. It's kind of a shorthand phrase, but it's kind of it's bad like language to use. What I meant to say was, or what me and my advisor kind of like just use.
Well, maybe you should preface it with what you were talking about. Maybe we can start getting into like the areas.
Yeah, my actual talk.
So what was your first topic?
My my whole topic deals with basically what's called the anomalous Hall effect and the anomalous Nernst effect.
Can we give people a little bit of a rundown of what the Hall effect and maybe the Nernst effect is, the normal versions?
Yeah, the Hall effect is this basic. Maybe you can have a little diagram here, but
yeah, I'm sure I'll throw it.
This basic effect that is governed by what's called the Lorentz force, and you have typically a current flowing through a sample or something, right? And you have a configuration of leads, is what we say, like it could be gold wires or something. They're fixed laterally, right? I mean transversely. Sorry, so they're like.
So you mean
sitting on the side of the sample?
Yes. So like if we imagine that the current is going in one direction, the leads of the wires would be perpendicularly connected on each side of the sample to the wire.
Exactly.
Okay. Maybe hard to visualize. I can hopefully put something in the podcast.
Yeah, this is why we use math and physics, because we skip all that stuff and then go straight to like the symbolism. But what happens is this guy Hall, what he found was that if you apply a magnetic field perpendicular to the surface of the sample, you will get this resultant force, right? And the force is expressed as, if we kind of look at the full expression, it's the charge carriers Q, typically how it's displayed. It's the magnitude of the charge Q times the electric field, right? That's generated plus again the charge, and then the velocity of the charge carriers and the cross product of with respect to the field. Now the cross product, for those of you that don't know, it's called a vector product or a vector product, which is basically you're looking at this how would you say, surface almost. That
I wouldn't get too complicated. I would just say maybe it's just you'll get a number with a cross product if your two vectors are perpendicularly to each other. If they're parallel, then you get zero.
Yes.
Yeah.
Beautifully said. And pretty much so what you should see is when the velocity is of the carrier. So basically you can sort of say that the velocity of the carriers are going to be parallel to or follow the direction of the current, right? So if the direction of the current is perpendicular to the field, then you're going to get a resultant force that pushes those carriers to the walls.
Right.
To the walls.
And this is not an obvious thing unless you've seen this in real life. Because I mean, it blew my mind. I never even knew that a moving charge with an external field would actually push or put a force onto a particle, right? But this is a technique they use all the time in experiments and everything,
Yeah.
And you can actually figure out a bunch of stuff with that. But anyway,
and so the carriers get pushed to the walls of this or the sides of the sample, and then they register on these. You also, like we were saying, you have these transverse leads on the side of the sample that are measuring what's called the voltage drop. So now you create this, because charges are going to one side of the sample, you're going to create a potential difference, right? And then you basically can measure this potential difference and then extract a bunch of interesting properties of your material.
So now your potential difference is a function of the magnetic field in some sense, correct? So now you can actually measure, like, let's say if you had a small magnetic field and then you were ramping it up slowly, you can kind of see that as you ramp up the magnetic field, you can kind of quantify it with a voltage value.
Yeah.
So anyway, that's the normal Hall effect. What
Yeah,
about
yeah.
the Nernst effect? I'm not even familiar with that
The
one
Nernst
at all.
effect is basically the analog of the Hall effect, but with a applied thermal field instead of.
Oh, interesting.
Instead of like the electric current, it's like
Yeah.
a thermal. I guess you could say it's a field because it's basically the del. It's a temperature gradient. It's the temperature gradient crossed with the field, the applied field. You know what I mean? Because you don't have necessarily a current. You're applying like a current density, basically, like if heat current density is probably. I'm trying to relate it in a way that you might.
Not sure I understand.
Okay, so I'll give you the experimental setup. This makes it maybe easier to understand. So what we did is you have a sample and you put a heater on one end and a heater on the other end, and this supplies your heat gradient, right? Your
So you have
temperature
two heaters. You just don't have like
Yeah.
a cold and a hot end.
You basically have that. So,
Okay.
Yeah. So you
The
have a heater
heater's
on
just to
one
make
end.
it, like,
It's just to
more
heat.
distributed or something.
So heat the sample on one end, and then you basically put a thermometer on the other end. It's like a heat source and a heat sink.
Yeah.
Right?
Okay.
So
one's hotter than the other one.
yeah. So you create a gradient in the sample, and this gradient
temperature
a
gradient.
temperature gradient.
Okay.
Sorry. You create a temperature gradient in the sample, and then you apply the field
Perpendicular
to the sample, and you should in theory see basically the Nernst effect. This is basically
Which is going to be the same as the Hall effect.
It's an analog.
Now where are the particles moving?
No, it's the same thing. It's just like the analog, but with instead of a current, it's a thermal gradient.
So then the hot particles are moving to one side, to the side of the wall of the material?
Yeah. It's the same thing. It's because the carriers, you're creating a how would you say?
Some kind of path of motion.
What do you mean?
Let me think. So what happens? So when you have a gradient of temperature, what does that mean exactly? That means that you have a bunch of jiggling particles on one end, and you have slower moving particles on the other end. So then that kinetic energy is being transferred from one side to the next side. So that kinetic energy means that there's going to be more bouncing between the particles. So what does that mean exactly? So then when you have a field, I guess, so that means that still there's movement of the particles. So the particles that they're jiggling so much, they're actually moving from one side to the other. And then since they're still moving like a current, so then you should measure a current as well. Is that true?
Well, you do measure the voltage drop. You do.
So there is a
thing.
current.
Well, yeah, but basically, like I'm saying,
the voltage drop is different though because
it's the thermal analog to the Hall voltage.
Yeah, but it almost sounds like with that thermal gradient, there's almost a current being generated. Do you know if that's true?
I wouldn't say the current is generated. I think like you're just applying.
So if you put another wire,
we're heating it through a current, for sure.
Yeah, you're heating it through a current, but that's kind of separate because you're really just heating. Like the sample stands alone, right? The sample's not connected up to like if you connected the sample itself, you're not going to read a voltage value at all. You're going to read. So let me try to say this better. So let's imagine there's just a sample, right? No heater, no nothing. If you connect a circuit to the sample, there's going to be no current. Just on its own. It's just in room temperature right now.
Okay.
The sample's just standing alone.
Yeah.
You connect it to a circuit, a battery or something. You're not going to measure any voltage drop.
You're completing the circuit with the sample in it?
Yeah. But it's just a standalone sample. Nothing is being generated. There's no
you're going to be
source.
but you're still putting current through the sample.
No. I'm saying no current in this case. I'm trying to build it from scratch right now.
Okay.
So then that's going to be no.
I feel like we're going
right?
to lose listeners here because we're complicating the picture. I just wanted to basically.
That's true.
I just basically want to say that this is the thermal analog to the Hall effect.
Okay. Yeah.
Stay with me on this.
Yeah. That's a good call. We're going down any lane.
Stay with me on this one. You can look at it as the thermal analog to the Hall effect.
Okay. Cool.
So what you find is that. Now, we all agree that the Lorentz force, what it does is pushes these carriers, right? And you should measure a potential difference, right?
Sure.
what you see though is that means that if you flip the sample now where it's in the field is applied in the plane of the sample,
yep,
you shouldn't see a Lorentz. You shouldn't see this force, right?
Oh, in the plane of the sample, as in like it's aligned.
The field is going now.
Yeah, you shouldn't see it.
You shouldn't see it, right? But this is where the anomalous.
Well,
part
maybe I
comes in.
actually could see something like there could be a bunching on that other wall now.
What do you mean?
Because
because V cross B, right? This is essentially what's happening. V is now parallel to B.
Yeah.
So
yeah, the math I can see, but I'm trying to think of it. It's weird for a thermal. It's kind of different. It seems like I don't know how I have to think about that logic.
Yeah, we can go into it like off screen.
Yeah,
we can go through it because like it's something that I was perplexed with too. I was like, what is?
It's weirder.
But nevertheless, yeah, it's what makes it anomalous is that for ferromagnetic materials, what you see is that this like Hall effect arises even when the field is applied parallel to the velocity or whatever the carrier's.
Interesting. Is it moving. A peak field?
No, it's just it's the same thing. Like if you apply the field linearly, you'll still see some weird behavior. For instance, like what we see for my particular crystal, and this has been confirmed in multiple papers. That was the first measurement I took, where the field as a response, because we were measuring resistivity, so Hall resistivity. So all that means, so conductivity, you can think about like how good something
conducts
electricity.
People know what conductivity
Okay, resistivity is the inverse of that. So nevertheless, we were measuring resistivity in the sample, and what we, as a function of field, and what we saw was that you reach like at low fields, about 1 Tesla, you reach this peak. And then all of a sudden, the sample or the signal, the resistivity starts dropping out
as you increase the field.
Yeah. So for most ferromagnetic materials,
it drops.
Yeah. So what you should see. So in fact,
you should see a saturation ideally, right?
Yeah. In most ferromagnetic materials, you should see a saturation, and then when fields are applied perpendicularly,
yeah,
they saturate, and you just say like, oh, that's typical ferromagnetism behavior, right?
And that all makes sense, right? Because it's like you're bunching of all of your electrons. It's just on one wall, and then eventually it's just there's no more electrons you can bunch against the wall.
All the moments are now aligned
Yeah.
in one direction. And in that case, like you're saying, like when we're looking at the analog of magnetization, I'm kind of piecing it together now. But basically, what physicists saw and observed for studying the ferromagnetic materials is that, okay, now we understand that there's this anomalous term. This was like in the early maybe late 1800s, I think, where they now were able to describe, we have this equation now. It's a linear combination. For the most part, it follows. So the first term follows the Lorentz force, which is typical of like Hall effect stuff. Plus another term where it follows the magnetization. And what I mean by that is if you measure how the moments behave inside of the material. So this has to do with magnetic domains. Magnetism in the purest sense is still an electronic. It's still a feature from the electrons, right? Because we're talking about orbital angular momentum,
right,
intrinsic spin, that kind of stuff. So magnetism, when the Insane Clown Posse asked back in the day,
this old meme,
this is an old ass meme. We're meme historians, Terrence and I.
I know, kind of, right?
So we know, but like when they had that question, what was it? Magnetism.
These signs are lying to me. Magnets, how does it work or something?
Magnets, how do they work? And it basically has to do with electrons. And there's a famous video of a scientist asking Feynman this question, and he got kind of pissed.
Yeah, he's like, why? What does why mean?
Which makes me think he didn't know where to start. He got pissed because he was like, bro, that's such a big ass question.
Well, he made an interesting point though, because he kind of said there were levels to why. He was being a little bit of a dick about it, but because he could have answered, but he gave a different lesson, which was interesting instead as well, which I kind of liked because you don't really see the answer he gives.
For those of you
often.
do you remember what the lesson was?
Yeah, it was a lesson of there's tiers of why. Like when somebody says, "I don't understand this," you can say like, well, what don't you understand about it? And they can have a more surface level answer, or they can have a deeper answer, or they can just keep going. The trail of why, it's kind of like the kids game where you ask your mom and dad like, why?
Yeah.
Why? And then they just keep asking why and why and why, and then eventually you're like, because the Big Bang happened, and it all ends in like the creation of the universe. You can keep going. So that was basically his
That's kind of what happened in my defense meeting, like, because my professor asked, "What do you like? Can you define what topology means to me?" And I was like, "Where do you want to start?"
Yeah,
it's like, do you want to start from like quantum mechanics and the set of axioms that you have to talk about and shit? Like, where do we begin? But nevertheless, that's a great point.
Yeah. That was Feynman's point, not mine.
Well, that's a great point by Feynman. But yeah, basically, magnetism is this effect that's it's intrinsic to the electronic properties of your material, right? Mm-hmm. So what you see is that when you measure the moments of the electron, you can in ferromagnetic materials particularly, you have this response where all the moments at certain temperatures, right? So for instance, for me, I have a paramagnetic material at room temperature, but once you go below a certain temperature called the Curie temperature, it transitions into a ferromagnet. So for ferromagnets, all the moments basically align. They point in the same direction. Mm-hmm. All the net angular momentum stuff, the L equals J plus S, all that stuff, they all point in one direction, okay? Mm-hmm. And what you see is that for paramagnets, it's the opposite. They kind of are randomly oriented, right? The domains are, because then you have magnetic domains, like basically isolated little islands.
Sure.
Where all the moments are kind of just like...
They're randomly pointing.
They're randomly pointing, but in the ferromagnetic state, they're all pointing in the same direction, ideally, right?
Yeah.
So yeah, so below a certain temperature, what you see is that all the moments are aligning, and this manifests itself as a saturation peak. So like as you're increasing the field, all the moments are aligning, right? Mm-hmm. They're all forming a line, and then once they reach a line, that means they're all participating now, and your magnetism reaches a plateau. And that's basically what you see when you measure magnetism as a function of the field.
Okay. I feel like we got a little bit off the beaten trail.
Well, I'm correlating it here with the anomalous Hall.
Okay.
So what you see is that you should see a plateau, and that's it. It doesn't, like, you can increase the field, and it'll just keep going, right? Mm-hmm. That's according to the theory. Now, what the anomalous Hall studies have shown is that, well, like, it seems to correlate with the magnetism in some way, like, because as we're measuring the resistivity values, like, they plateau. You know what I mean? And so that's what they observed. There's like, oh, okay, so you can draw these two and they say, oh, it plateaus as a function of the magnetism as well. Mm-hmm. The magnetization of the sample. So they thought they figured it out. Mm-hmm. They're like, we're done. Mm-hmm. Cool. But then, of course, scientists' job is to break that and like look at other configurations and see. And so, what they saw is for some materials that if you, especially for mine, the same thing that we see, we kind of like, the thing that makes this anomalous in particular is that if you measure along the field, the field along the plane of the sample, you still get this like effect that when there's no Lorentz force, right?
Yeah, why
it's
is
like,
that?
It's like, why is that? Yeah. It's like, why is that?
And is there no answer?
Well, the thing is, the theory is like the new theory within the past 20 years or so is that it has to do more with the geometry of the band structure. So the way the band structure is, So the way the band structure is because it was there's a lot of stuff that's insufficient in describing like what exactly is going on. Like one competing theory one theory that was proposed like 2015, I think. 2016 was that because what we saw was that the magnetization it hits a peak at low fields, but then the resistivity goes up, but then all of a sudden it starts dropping. So but this is for the resistivity, not necessarily the magnetization. The magnetization, that means that the anomalous Hall effect is supposed to follow the magnetization, but in our data, it doesn't. They're supposed to be correlated. They're supposed to be 1-to-1.
Okay.
Right? For the most part.
Okay.
That's what the theory says. But they don't.
Okay.
The resistivity, the Hall resistivity is showing like this weird behavior where it looks like a peak. It looks like a little mountain peak, and then it just trails off to basically zero.
Now, does this have anything to do with the sample size?
No, actually, what's funny is that there are some people that were saying, well, it could be that we know that the magnetization axis for this particular compound is what's called the easy axis. So, like, some samples have like an axis that's a crystallographic axis that's preferential for magnetism, pretty much for magnetization. So, like, you could say that that's where the moments want to go or point.
Right. So if you have an externally applied field, it's going to most likely align to that easy axis.
Yeah.
And the antithesis to that would be the hard axis, correct?
Yeah.
Okay.
So there's some crystallographic data that's collected by neutrons to kind of tell you what the structure of your crystal is, like a deeper, meaningful structure, like not like X-ray diffraction. That just tells you like what the parameters of the crystal are, the spacing and shit. But this,
I thought it shows you the structure as well.
Neutrons?
No,
it does.
No XRD.
It does.
Okay.
But I'm saying like it tells you neutron data. I think shows you more details, more fine.
Oh, a
more
different
fine.
kind of thing.
Yeah, because I think
because it doesn't interact electrically.
I believe so. Yeah, it gives you more.
It only hits things atomically, right?
It's supposed to give you more details about it, about the electronic structure of like where things are.
That makes sense because there won't be any electronic repulsions anywhere.
Right.
It's going to be like almost purely atomic.
I am not an expert in neutron stuff. I don't work with
You're
neutron.
talking it bombards the crystal with neutrons is what you're saying.
Yeah.
Okay, yeah.
I don't do neutron diffraction stuff.
I never heard that until you just said it. But it kind of
makes sense.
Oh, okay.
Yeah.
Yeah. So I'm just reading the paper. They argue that this particular crystal, it's a collinear ferromagnet, meaning like the field, I mean the moment is pointing along the it's basically along the c-axis. But then what this other group was proposing in competition to that was that you basically have these non-coplanar like spins or whatever. What I mean by that is that they're saying that there's the easy axis where the spins are aligning in the perpendicular to the plane of the sample. But when you apply the field, they're kind of like decanting in the plane. So they're kind of like the moments want to do this. So they kind of, I don't know if you can see this. Oh man, I have to talk.
What does decanting mean?
Decanting means it's like slightly slanted. The spins are like slanting into the plane a little bit.
Okay.
They're not like completely in the sample plane.
Yeah.
But they're like, there's an angle between the sample plane and the magnetization axis.
And it's something about the crystallography that makes it do this?
That's what they're arguing.
Okay.
But the neutron data...
It's getting more complex
It
now.
is. But the neutron data is basically saying, no, that's not what it is. But they're arguing that, no, but this is what could explain what we see.
So there's a little bit of disagreement between the two different ways of measuring these kind of effects. I see.
Yeah.
Interesting.
So
they're still building the mental picture.
They are.
I got you.
And the thing is, this is supposed to be a simple ferromagnetic system, but it's clearly not. Like, it's
this
clearly...
is an interesting material.
It is.
How many other groups are interested in this?
Bro, like everyone's asking me for crystals. I've sent like crystals to like 3 different groups, 4 different groups. I don't even know who I sent
people are
samples
hungry
anymore.
for this thing.
They are. And
Interesting.
so I'm like, okay, all right. So I basically like a crystal grower.
Are you guys one of the only people growing them?
No, there's plenty of other groups.
Okay.
I think because they're in demand, and so I know of 2 other groups in our. We're probably the only group growing it in our department.
Yeah. But I mean, like in the U.S. or the world.
Oh, I see. Well, particularly at the school, I think there's somebody in the chemistry department that's growing them.
Oh,
and I'm like, okay, competition.
Or an extra resource in case you fuck up, you just go get some of their crystals.
No, but I generally figured out the recipe. I have a decent recipe. I'm supposed to go take out some crystals today. Funny enough, but yeah, so yeah, there's like a competing.
Can you grow meth?
Sorry, I just had to.
I can, but should I? No, I shouldn't.
All this talk of crystal.
Yeah. I could, but I shouldn't. So I use my powers for good.
The Eigenbros are opening a meth store.
Yeah, you can be the Gus Fring of the Breaking Bad, basically. But yeah, the thing that so anyway, so there's these competing theories, and there was a couple of groups who decided, F that, we're not going to go for these sort of semi-classical kind of approaches.
Mm-hmm.
We're going to use some more new, basically, well, not, when I say new, I mean relatively new within the past 20 years. There's been a development by Dr. McDonald over at UT. I think he's still at UT, at University of Texas in Austin, and him and a couple other people, they put together this like really good review paper on like the anomalous Hall effect and how there are different descriptions of it. And right now, I think the one that's more sufficient in capturing like what's happening or what's being observed is using Berry phase concepts. So they're using concepts that have been developed in the recent modern physics, 1980s or so, and yeah, so they're kind of like, and it's been actually pretty decent in approximating like what's happening. So like in this particular paper that was published in 2018, with respect to my compound, they were saying, oh, we can use like these Berry phase concepts to look at the Hall conductivity, and they basically go into the theory and say we know that we can talk about how the Berry phase or this like this mathematical like construct of how would you say, or feature of the wave function, right? How you can describe what's happening electronically.
Okay, maybe you should get into Berry phase.
Yeah. So Berry phase, I'm trying to strip it down to like its more digestible form, because typically when you talk about like band structure stuff, you kind of get these toy models.
Okay.
That you play with, like particles in a box kind of stuff.
Sure.
Like the more simple particle in a box stuff that you see is like you have a Hamiltonian, which is like the total energy of the system, right? And then, famously we do this. This is the most exciting part of like quantum for me, but it was when you're trying to find the wave function. Yeah. What did they call it? I forgot what they call it.
What?
For those people that kind of want to investigate this, I forgot what they call the process. I think it's called
just solving the Schrödinger equation.
No. You find the actual wave function like the parameters that fit the wave function to the Hamiltonian. Do you remember this process?
I just call it solving the
for the wave function. What else?
But it's like I guess. But there's a certain feature. If you go to Griffiths, yeah, I think it's in Griffiths or something.
Beats me.
Yeah. Okay.
Leave it in the comments if you know what the hell Juan's talking about.
I was hoping that because it's so cool. But basically, what you do here is kind of similar. You build a wave function for your system, right? And then you start finding some of the features and for it depends on your particular compound. But anyway, you basically get an energy spectrum or energy spectra for this particular wave function, and in condensed matter physics, we typically model them using like block wave functions, right? Which is, I think, something we talked about, but it has to do with like.
I don't even want to.
But let's just say there's certain types of wave functions, and here you're working in momentum space. You're working in like in this particular space that has certain meaning for like what K is supposed to be like. I think in E&M, K is supposed to be like a wave, the wave number or something.
This is a different version, though, right?
But it means it's different with respect to the block wave function.
Right.
Like
K is like the crystal wave number or something. Yeah.
But basically, I don't know how. See, this is the thing. We can get into so much detail, but basically, you can look at what electrons, the states. You can look at the eigenstates. And basically the energies that correspond to the states of the wave function.
Okay.
And you can build a sort of map of the space, right?
Mm-hmm.
So the wave functions, actually what that guy Barry showed was that typically typically in physics, typically in what we did previously, or what physicists did in the past, was kind of ignore like this phase factor that you attach to wave functions that you built in, because because physicists love doing this all the time, this hand wavy shit where it's like,
it repeats, right?
Yeah, because it's like, you can always shift everything off by a phase and get it to normalize,
right?
Whatever. Real easy peasy stuff.
The less shit we got to keep track of, the better. That's why the whole natural numbers even came from. Natural units came from.
Yeah, yeah. And like I said, I'm trying to strip it down to its like essence, but so I'm going to skip around and skip all the details. But this guy Barry, he basically was like, no, for you actually can sometimes get a non-zero value for this phase. Like you can actually. It's not just trivial. You can't just throw it away sometimes, especially if it's a closed two-dimensional surface. And that has to do with like this famous theorem called the Gauss-Bonnet theorem about 2D surfaces. And you can look up like how closed surfaces have this weird property where they're quantized by 2 pi, meaning like they're like, how would you say, they're factors of 2 pi. Like
right, it has something to do with the lattice oscillations, correct?
Yeah, I think at some deeper level, yeah. So like the thing is, what the Gauss-Bonnet theorem says is just like, you can have two, like, whatever. As long as you have a closed two-dimensional surface, you get this property where your surface is it's something multiplied by 2 pi.
And if you have something popping out that has 2 pi or anything with pi in it, you can rest assured it's got something to do with circles. And if it's got something to do with circles, then you know it has something to do with periodicity, most likely.
Yeah.
So like all that stuff makes sense when you get used to seeing pi everywhere.
And so they saw this and were like, oh, okay, well, most states that we're talking about in the states of the wave functions that we have in
1 hour later.
And so what they found was that there's like an analogy, or you can draw an analogy between this result where it's like you get a quantized, like, nice little number, and then what you do is they started looking at how this line integral starts looking like magnetic, like the magnetic flux, pretty much.
Okay.
Do you remember when Maxwell's equations, when you take the line integral and stuff, and you can do like...
Yeah, you can do it with the del cross E.
Exactly.
Right, and you can get the change in the magnetic flux.
Exactly.
If you, multiply it by the differential area.
Yeah, exactly. So this is the kind of connection they started drawing, and then you talk about gauges and shit, because now you're starting to talk about magnetic fields, and so like they started analogizing this system, meaning like Barry phase stuff started looking like magnetism in some sense. And so basically this is where the theory started going deep. And they started saying like, well, now you can look at this as a sort of like the Barry phase kind of creates this like magnetic field, and you can create basically like what looks to be like monopoles and stuff. And in this space, right? And so what I mean by that is like you can have anti-symmetric pairings and symmetric pairings, and so they cancel each other out. So it's like it's not just going to exist out of nowhere.
Right.
So whenever
it's like a pseudo monopole.
Yeah, it's like a sink. You create if you have a source, there's necessarily a sink. So they're always going to.
I think I heard about this stuff way back when I was doing undergraduate research, but then I never really never stuck because I didn't know what it was.
Yeah, it's like. The level of knowledge you have to build is like insane, but yeah, they pretty much, that's what they kind of found, was that we can draw analogies between this, and then we have these weird, interesting, like physical things happening. And so pretty much they were on the search for this kind of behavior, and sure enough they found these kind of things, and now they were beginning to be able to describe certain stuff that had been theorized, like Weyl nodes, which you'll talk about, which nodes, for those of you that don't know, are basically basically points in space, but in 3 dimensions. So you have like, if you're talking about momentum space, it's like K sub X, K sub Y, K sub Z, right?
A node has to be three-dimensional?
Yeah, I believe so.
Okay.
Because the point is...
This is a different kind of node than probably what I'm understanding then.
Oh, what do you mean?
Because I'm thinking of
like
just
standing
nodes.
wave stuff?
Yeah.
Gotcha. Yeah. Well, I mean, if you talk about a standing wave in 3 dimensions, then I guess like you can kind of say like the nodes are...
Yeah, but this sounds like a node that's been promoted to a new meaning or something.
I think the... Yeah, because you create... Well, they call it like band crossings. You get these like... When you map the energies of the system, the crystal system, and then you look at different points in space, this is where you get into like Brilliant zone shit. I'm not going to go into it because let's just say...
already gone through this
let's
before.
just say you look at one region of the crystal lattice that you've defined already, and you look at all the symmetry points. You look at certain points in K space, in momentum space, which is where the crystal... That's the picture we typically choose out of convenience. Now, Terrence has always asked, why don't we work in real space?
Yeah.
Which
we were debating this off camera before.
But I think it's because real space kind of makes things wonkier.
Yeah, I'm sure it is.
Yeah.
I'm sure K-space is much mathematically better.
Yeah.
And it probably is much more insightful and useful, but...
Yeah,
Of course, the higher abstraction you go, the more the image starts, the less it makes sense on the front end.
Yeah, the real space images.
Conceptually.
Yeah, because you're losing the mapping of what reality, what it's supposed to look like.
Exactly.
Yeah.
Those are always very hard stuff to analyze.
Yeah, 100%,
Yeah.
man. I totally get it. And
So,
it's so anyway, you kind of get these you kind of get this like what you can say is you can build a 3D map of the energies in this space, and you create surfaces, and like if so you have conduction bands and valence bands. I'm sure you guys have heard of all this. If you want to get really, if you really want to be a stickler to it, the difference between the valence band and conduction band has to do with like this thing called the Fermi energy, and that's dependent on the material. You talk about like how many states are building up, or how many states you have occupied in your whole system electronically. And that's
What's the Fermi energy again? It's very simple too, isn't it?
Yeah. It's
What
like
does it
basically
mean?
how many states you can fill up at the t equals 0.
Oh, okay. There we
Yeah.
go. Thank you.
Yeah, so it's like quite literally like how you partition those, and then what you'll see is that for metal compounds, like you'll have an occupied. So you'll like if you look at the band structure of this, these spaghetti looking models, you'll have basically one band kind of dipping into this. Well, let me describe a semi-metal actually. Because I think the semi-metals are all really, really illuminating. So like you have a band crossing where it's like above the Fermi energy, but then it dips below this Fermi level. That's like line. Let's just say you draw this line and it dips below and it comes back up. That's called an electron pocket, pretty much. An electron's occupying that, and that's the valence band. They're occupying that valence band.
Okay.
And then you have this other thing where it's below the Fermi energy, but it's like anytime it goes above this line, you create a hole where an electron can occupy that, pretty much.
Okay.
So that's kind of, if I remember correctly, that's pretty much the distinctions. And you can kind of build like a picture, because this is a semi-metal. So a metal would just be like the conduction band is all filled and shit. So anyway, so yeah, you create this like, so you can think about these bands as three-dimensional surfaces, and then the word topology comes in because you talk about the geometry of surfaces. And this is what we mean by topology in general. Like,
and topology comes from mathematics.
Right. So it's a study of surfaces, essentially.
Surfaces, yeah. So I got in trouble because I said
I forgot that was the whole lead up. All this.
I got in trouble because I said topological magnetism, and then they were like, "What?" And then I was just like, "Oh, I guess I meant to say like topological origins of, or the origins of magnetism are probably topological in our compound." And they were just like, "Yeah, it makes us worry that you don't know what you're talking about." And I was just like, "I'm sorry." I was like, "My bad." I was like, "Yeah, okay." I'm just like, and the whole community is like, one of the professors was like, "Look, the whole community uses terminology like this, all the loosey-goosey kind of stuff. We just want to make sure you don't do that." And I was just like, "That's fair." So yeah, it was like, because you're trying to capture headlines.
Right.
You know what I'm saying? Like,
right.
you're trying to get people to read your paper, so sometimes you use phrases like, all right, let's see what the fuck this person's doing. and yeah, so guilty of that. And
that whole lead up was just was to say that you that you got in trouble for saying topological magnetism.
I know, dude. I know.
I think when it's literally like the time for the podcast. But that was good though.
No. I still want to talk more. I have like 10 more minutes.
Okay. Yeah.
So I'm gonna wrap this.
But I'm looking at an hour, right?
Yeah.
Okay,
you're
so
right.
we're on the same.
Yeah. So like, so kind of just to wrap it up. Mm-hmm. You need necessarily you're starting to need these like higher concepts to describe what's happening in the system. In particular, for me, like one of the professors asked, "Well, what can you point that's uniquely like something that might have to do with like the topology of the system more than like anything else?" And I was like, "Well, necessarily for me, the Nernst, because what we see with like our Nernst stuff is that, or Nernst data is that." You have it following the anomalous Hall up to a certain point. What we see in the anomalous Nernst is actually confidential information. Sorry, everybody. You're like, what is? And in fact, we got this result like in 2018, and my advisor was like, I don't believe it, because we were two lowly graduate students doing this. It was me and this other Brazilian student. Shout out to Danilo. You know, he's in Brazil right now.
Does he watch the podcast?
I don't know, but shout out to him.
Not.
He's thank you for helping with that measurement, because we were both like, dude, I was like, bro, I have no idea. You built the probe. He built this like probe and stuff. Mm-hmm. And then I was just like, I mean, look, bro, I'll take measurements, you know, I'll supply the crystal and stuff, and then do all this stuff. But he like, yeah. So we took a couple data points, a couple curves, and then he like refined it and was like, bro, this is real. And he like rechecked it, but our advisor was like, I don't believe it. And then it basically took another year, because we kept trying to redo our data and then like take more measurements. And then what we did is like, now we took a profile of the signal. This information is confidential. My advisor is scratching his head. I'm just like, dude, I got classes to take and I have to teach. I'm sorry. Like,
right.
And so,
no time to think.
Yeah, I'm just like, bro, I'm sorry. Like, I can read a couple papers, maybe see if I can find something. And yeah, so he gets another graduate student to confirm the results. He's a little bit more skeptical. He's like, bro, this probe is fucked up or something, and blah, blah, blah. He's like, it's leaking heat.
Yeah.
I can't trust it. And so, so he like fidgets with it, but, you know, a month passes by and he's like, oh shit, actually, I'm confirming what they're saying. So he kind of confirmed it, but then my advisor still didn't trust it. And so then he went to, now he's kind of gone to a more professional guy in our lab. And like, he's an expert in these kind of measurements. And so he's confirmed it. He's like, bro, we're going to bring you on to do this paper, because we need to like really confirm that this is real. And so, yeah, what we see is like legitimate, and
So is it a big deal?
It kind of is. And, but the thing is, it's not escaping the realm of explanation. Like there's a paper out there where they looked at this certain topological material, that where it's like magnetism might be attributed to the sort of the structure of the band structure of it. So the geometry of the topology of the material, yeah, the band topology. So it's like it's manganese 3 tin, and in this particular paper they kind of laid out some of the theory and saying just like, you know, this is more conventional and it's supposed to follow this, but it's described by the math. And so we were looking at that paper as a reference. But what we see is like, we're trying to describe what happens. Information redact. Contributing or dominating at a certain point, but why? Like, it's not necessarily being captured in the equations. It's like there's something deeper happening there that is like what? It's not showing up in other things. You know what I'm saying? And other measurements that we have that corroborate our findings. And It's like it is an ambitious project. It's a hugely ambitious project, and I think they kind of gave shit to my advisor because of that. They were just like, "Bro, this is not a master's project."
Hey, but it can be good for PhD maybe.
Oh no, it's a beautiful beginning to a thesis project.
Yeah.
I think I have pretty much like 70% of it.
Oh, there you go.
But it's like they even were like, "What the fuck, man? What are you making this graduate student do? He's just supposed to do a master's thesis."
Well, that's good because now maybe you'll be
Back on track.
Mm-hmm.
So yeah,
So anyway, that's pretty much my research in a nutshell.
that was good. That was really good, Juan.
Yeah, thanks.
Yeah, it's interesting. That's the most I've learned about your research, I think, actually.
I don't know why I'd ever asked you about it before.
Well, because I wanted to save it for the podcast, so this is good. This is
There
good.
we go.
But yeah, if you have any questions, I guess,
We got an expert right here.
go look at some papers. Don't ask me. I'm tired of looking at this. No, I'm just kidding.
Yeah, I've learned some good things today, though. Anomalous Hall effect, and well, I've heard of Anomalous Hall, but Nernst effect is very new to me, so I'll have to look those up now.
Yeah.
So
Cool
yeah,
stuff. Yeah.
So yeah, guys, stay for the outro, and we'll talk a little bit more over there.
Mm-hmm.
Thanks again, guys. So that was a nice little episode of Juan's research that we had. Hopefully, it was enjoyable. Of course, we never know until we see what the comments say. But I think it was pretty. We kept it pretty tame. I want to say.
Yeah.
Hopefully, interesting enough. But yeah, guys, if you want to ask Juan any questions about his research, leave the comments below. We'll get to him. I'll let Juan know about it, and I'm sure he'll be able to give you some expertise, maybe some resources even. And yeah, guys, just make sure to like, share, subscribe, comment. Am I missing anything, Juan?
No, just follow us on our socials too.
Yep. So follow us at eigenbros.com, Eigenbros on Twitter. Instagram is Eigenbros, and then we have TikTok, Eigenbros 2, and we'll see you guys next time.